Welcome to today's Explainer. We are jumping right in because today we're embarking on a pretty fascinating journey to uncover exactly how researchers go beyond just, merely observing the world to rigorously proving cause and effect. We're going to break down the exact anatomy of a perfect experiment design, exploring the hidden gears and levers that make these scientific studies actually hold water. And we'll be spending a really good chunk of time unpacking one of the most powerful tools in modern behavioral research, the study vignette. We're going to see exactly how experts construct these highly controlled, simulated realities to test human behavior in ways that everyday observation literally just can't match.
So here's the big question. How do you prove that X actually causes Y? I mean, we live in a world completely bombarded by confident claims, right? Every single day there's a new headline insisting that drinking 3 cups of coffee causes you to live longer, or that some trendy new management style absolutely skyrockets workplace productivity. But think about your own life for a second. When your company rolls out a new policy or some diet guru tells you to cut out a specific food entirely, how do we move beyond simply guessing? How do we definitively separate a random coincidence from absolute, undeniable proof that one specific thing caused another? Well, finding the answer to that is the entire foundation of rigorous research. It's an incredible puzzle, and it's exactly what we're going to solve together today.
Okay, let's dive into this. Here is our roadmap. 1. The quest for causality. 2. Anatomy of an experiment. 3. Designing the perfect vignette. 4. Between and within subjects. And 5. Analyzing the data.
All right, Section 1, the quest for causality. This quest, it is the fundamental, driving goal of all social scientists. It's basically the holy grail of behavioral research. As researchers like Antonakis point out, social scientists make causal claims, statements like X causes, predicts, affects, influences, explains, or is an antecedent of Y. Finding these definitive causal links isn't just some fun academic side project, it's the ultimate prize. Because let's be honest, in the messy, incredibly complex environment of human behavior, it is remarkably difficult to say with total confidence that your specific intervention and absolutely nothing else drove the change you're looking at.
And the reason it's so incredibly difficult really comes down to a massive logistical hurdle known as the counterfactual argument. By definition, a causal effect is the observed outcome after a treatment minus the unobserved outcome that would have occurred without it. To really wrap our heads around this, think about having a splitting headache. You take an aspirin, right? And 20 minutes later, your headache is gone. Did the aspirin cure it? Well, to know for absolute certain, you need to compare your pain level right now with the pain level of a parallel universe version of you who didn't take the aspirin at that exact same moment. But we obviously can't observe both realities for a single person at the same time. So we have to find a way to scientifically and mathematically approximate that missing, invisible reality. That's our counterfactual. Which brings us to a major dividing line in how we gather information: survey studies versus experimental designs. Think about those employee satisfaction surveys you fill out at work, or quick online polls. They are fantastic for scooping up huge amounts of data, but they're generally just correlational. They have very limited control. Basically, they just show us that two things are moving together, kind of like ice cream sales and sunburns. They completely fail to establish a true cause and effect relationship because you can't control the weather or the temperature or 1,000 other outside variables. Experimental designs, though, they step in to save the day. By using tightly controlled settings, a great experiment design actively builds that missing counterfactual we just talked about. It effectively simulates that parallel universe so we can isolate the exact relationship we actually care about.
Moving right along to Section 2, Anatomy of an Experiment.
So how do we actually build these highly controlled environments in the real world? Well, every true experiment rests on 3 totally non-negotiable pillars. Number 1 is manipulation. This is where the researcher actively changes the independent variable, rather than just sitting back and passively observing it. If you want to know if background music improves memory, you don't just find people already listening to music and test them. No, you actively create 2 environments, one with music, one completely silent, and you put people in them. Number 2 is random assignment, and honestly, this is where the real magic happens. Every single participant must have an equal chance of being in either group. Why? Because if you let people choose their own group, all the naturally focused students might just choose the quiet room, completely ruining your data. Random assignment magically smears both known and unknown human differences, like age, how well they slept, baseline intelligence, evenly across your groups. And finally, number 3, control. You absolutely must hold all other potential influencing factors constant. If the music room is brightly lit but the silent room is pitch black, your experiment is toast. You've just introduced a completely new variable.
Let's walk through exactly how those 3 pillars come together to create a counterfactual. Imagine 40 individuals arrive at a lab. Unbeknownst to them, they're randomly split into 2 groups of 20. Boom, there's our random assignment ensuring both groups have a similar mix of tired folks, energetic folks, and everyone in between. Next up is the active manipulation. One group is shown a funny event on a screen, while the other group watches an ordinary, super mundane event. Finally, both groups sit down to complete the exact same reasoning test featuring 10 logic problems. Because everything else in that lab, the lighting, the temperature, the test itself, was held strictly under control, if the group that watched the funny video performs significantly better or worse, we don't have to guess. We can state with absolute confidence that the type of video caused that difference in performance.
Which leads us perfectly into Section 3, designing the perfect vignette.
But wait, what happens when we can't easily manipulate something in a physical lab? I mean, we can't exactly force a real-world CEO to behave entirely differently for 6 months just to see what happens to their employees' morale, right? This is where we turn to the study Vignette. These are simulated, highly calibrated real-life scenarios presented as text, video, or audio to participants. Consider a text scenario crafted for a study looking at how a leader's fun pursuit affects employee perception. The participant is asked to imagine working in a digital marketing team where their leader, let's call them Ella or Sam, is described using incredibly specific phrasing. It might say, Ella always approaches work goals in playful ways. The researchers are literally building a hypothetical world here. By carefully crafting this specific text, they're executing that manipulation pillar we just learned about. They isolate a single variable, a fun leader, while ensuring the industry context, the team's tenure, and the specific job description remain perfectly constant for every single person reading it.
Writing these simulated realities, though, is an incredibly delicate balancing act. You can't just slap together a quick fictional story and hope it spits out good data. There are strict core rules. First off, you must avoid abstract or overly artificial descriptions. If the scenario feels alien or fake, the participant won't mentally buy into the simulation and your data is basically useless. To get that authenticity, researchers often use prior materials, actual interview transcripts, or weave in real workplace dialogue and common conflicts. You also have to include just enough safe background detail to make the world feel lived in and immersive. But, and listen, this is the real danger zone. You have to be relentlessly careful not to accidentally contaminate your main manipulation. If you describe the fun manager as also being super generous with end-of-year bonuses, you've completely muddied the waters. You no longer have any clue if the participant likes the manager because they're fun or just because they pay well.
All right, Section 4, Between and Within Subjects.
So, you've got your experiment or your carefully crafted study vignette all ready to go. Now, you have to decide how you're actually going to structure the human beings participating. Generally, we've got two main structural choices here. First, we have a within subjects design. In this setup, the exact same person experiences all the conditions. They're exposed to Scenario 1, and then that very same individual is exposed to Scenario 2. The huge advantage here? The person acts as their own baseline, which completely eliminates individual differences. The downside is they might catch on to what you're secretly testing. Alternatively, we have a between subjects design. Here, different participants are completely isolated into different conditions. Person A only ever sees Scenario 1, and Person B only ever sees Scenario 2. This totally prevents participants from comparing the scenarios, but it does mean you need a much larger group of people to make sure random assignment does its job properly.
And that brings us to our final stop, Section 5, Analyzing the Data.
You've built your counterfactual, you've randomized your participants, you've run the experiment. Now, we cross the finish line by actually measuring the outcome. To do that, we have to match our experimental architecture to the correct statistical formula. Think of it kind of like a sorting hat. You don't need to be a math genius, you just need to follow the logic. If you chose a between-subject design like we saw with Person A and Person B in completely separate groups, you're going to use an independent t-test to compare those distinct groups, or an ANOVA if you have 3 or more groups. But if you went with a within-subject design where the exact same person experienced everything, you absolutely must use a paired t-test. Making the correct analytical choice right here is what ultimately solidifies your proof.
Let's ground this with a concrete narrative of how this analysis looks in action. Let's use the fear of statistics test, or FOST intervention. Imagine a student whose confidence is incredibly low because they are absolutely terrified of taking a statistics course. Researchers measure that student's exact confidence level at time 1. Then, they apply an experimental teaching intervention designed specifically to reduce that anxiety. Finally, they measure the exact same student again at time 2. Because we're measuring the same person twice, this is a repeated measures design. By properly analyzing the change within that single specific student from time 1 to time 2, researchers can mathematically prove whether their new teaching method actually caused the fear to disappear. And that brings us to the end of our explainer on causality. We've seen exactly how rigorous manipulation, the clever, delicate design of study vignettes, and precise mathematical analysis allow researchers to completely separate casual correlation from undeniable causation. The true power of a great experiment design is that it cuts right through the noise. So I want to leave you with this thought to carry into your daily life. Next time you see a flashy news headline claiming a new trend definitively causes some spectacular result, will you ask to see the experiment? Will you actively look for the control group, the random assignment, and the counterfactual? Empowering yourself with this knowledge literally changes how you read the world. Keep questioning, stay curious, and keep learning.